So the next reaction we're looking at is called an oxidation-reduction reaction, or we also call it a redox reaction. So in a redox reaction, two things occur. Oxidation, which means something loses an electron, an atom or an ion loses an electron. And then reduction also occurs, and that's when an atom or an ion gains an electron. So both of these things have to occur in a redox reaction. Most of the redox reactions are combination, decomposition, and single displacement reactions. So the reaction there on the slide is a single displacement reaction. So you have zinc and copper. So zinc is a solid, copper is aqueous, so that's in the solution. So if you look at the picture, that first test tube with the blue solution, that is the copper in the solution, okay? And then you can see, up here is the zinc before it reacts. Okay, obviously in the test tube it's reacting. But the metals just change place. Okay, so the copper begins to become a solid, and the zinc goes into solution, and you can see in this middle picture here that blue color is fading because the copper is coming out of solution and becoming a solid. And then here in the last picture, the blue is completely gone because the copper is no longer in the solution. It's only a solid now, and the zinc is now in the solution. So anyway, that is a redox reaction, and we can see with the chemical equation that it says zinc is losing 2 electrons. So zinc is being oxidized because it's losing electrons, and copper is gaining 2 electrons, so that copper was reduced. So that's a little confusing sometimes, because when we think we've lost something, we think of reduction, but here you're gaining electrons. So you can remember oil rig. Let me do that over here. Okay, oil rig. Whoa, I just went to a highlighter unexpectedly. Okay, so oil rig means oxidation is lost and reduction is gain. So that kind of helps to remember, what does it mean when we're losing electrons? What does it mean when we're gaining electrons? What is, the word for that? So that's just to help. Okay, so again, something is losing electrons, something is gaining electrons. So in order to figure out who is losing, who is gaining, we use what's called oxidation numbers. So we give the elements hypothetical charges to help us determine who lost electrons, who gained electrons. So I'm going to show you an example here, and then I'm going to go through the oxidation rules. So the oxidation number on calcium is 0. On oxygen is 0. Okay, on calcium here it's a +2, and oxygen is a -2. Okay, so for calcium, we're going from 0 to +2. Okay, in oxygen, we're going from 0 to a -2. Okay, so remember, electrons are negative. So if my number is going to be more negative, and that means I'm gaining electrons. Okay, so that would be reduced. And if my number goes from to a more positive number, then I'm losing electrons. And so that's what was oxidized. So for example, calcium goes from a 0 to a +2. So my number's getting more positive. Okay, so that would be that it lost electrons. Oops. Let's try that again. Okay, and then oxygen is getting more negative, so we've gained electrons down here. Oh, to write electrons. Reduced. Okay, so I'm going to go through these oxidation rules. They're kind of frustrating sometimes because it's like, well, it could be this, it could be that. So we'll go through these rules, and hopefully once you start using them, it'll make it a little easier, but kind of in the beginning, it's a little confusing with these rules. Okay, so if I have an element that's all by itself in a chemical equation, the oxidation number for that is 0. So those are easy. Let me just come back here. So that's why calcium and oxygen, their oxidation numbers were 0, because there's no other element with them. They're all by themselves. So even oxygen, it has 2 oxygen. Okay, it has 2 oxygen here, but it's still just oxygen. There's nothing else with it. So the oxidation number was 0. Same thing with calcium. It's all by itself. So the oxidation number is 0. Okay, and then if you have an ionic compound, then you can just use the charge of that ion for its oxidation number, as long as it's a monatomic ion, which means as long as it's just an element and not a polyatomic ion. Okay, so if I have a polyatomic ion, let's just say sulfate, SO4 -2, I cannot use -2 for the oxidation number of sulfate. So I'm going to have to break that up into sulfur and oxygen. Okay, but if I have something like calcium chloride, okay, well, calcium's charge is a +2. Chlorine's charge is a -1, but I have 2 of them, so I do 1 or -1 times 2. So it'd be an overall -2 charge. Okay, halogens are usually -1, and fluorine is always -1. Okay, but the chlorine, bromine, and iodide can have different oxidation numbers. So that's where it gets kind of annoying, because the oxidation numbers can change. So it says when halogens are combined with oxygen or fluorine, the oxidation of chlorine, bromine, and iodine is not 1. So in this first one, we have CF4. So fluorine has an oxidation number of -1. So it should always have a -1. And then on ClF3, so fluorine is going to have a -1, which means chlorine is actually going to have a +3. So I'm going to go through these and you'll see how to figure that out. But you should always know one of the elements' oxidation numbers so you can figure out the other one. Okay, and then Cl-, we have oxygen. Oxygen's oxidation number is -2. Okay, that changes too, but in this one right here, in this example, it's -2. So that means chlorine will have a +1. Okay, so fluorine, always -1. The other halogens are -1 unless they're paired with oxygen and fluorine. Okay, oxygen has an oxidation number of -2, except when it's in the peroxide ion, then it has an oxidation number of -1. So we don't see the peroxide ion a whole lot. So usually oxygen has an oxidation number of -2. Okay, hydrogen, when it's combined with a metal, has a -1 oxidation number. And when it's combined with a non-metal, it has a +1 oxidation number. So the way I remember this is metals are usually positive. And if I'm going to pair hydrogen with a positive, it has to be a negative. So I think -1, okay? And then non-metals are usually negative. So if I'm going to pair hydrogen with the non-metals, then it needs to be a +1. So that's kind of how I remember those two. Okay, and then the sum of the oxidation numbers for a compound are going to equal 0. And then the sum of the oxidation numbers for a ion are going to equal the charge of the ion. Okay. Okay, so let's do some examples here, and I think hopefully that will make more sense as we do the problems using the rules for oxidation numbers. Okay, so first we have H2S. So we want to know what is the oxidation number for sulfur. Okay, so hydrogen, we know, has a positive one when it's combined with metals, and it has a negative one when it's, I'm sorry, I said that wrong. Hydrogen has a positive one when it's combined with nonmetals and a negative one when it's combined with metals. So here, sulfur is a nonmetal, and so it's going to be a positive one. Okay, so positive one, and there's two of them right there, so times 2. Okay, we're going to solve for x, so plus x, and we're going to set these numbers equal to 0. So a neutral compound, the oxidation number should add up to be 0. Okay, so this gives us a positive 2 plus x equal to 0. And if I move the 2 over here to get x by itself, then the charge or the oxidation number for sulfur is negative 2 here. Okay. And then on B, we have S8. So even though I have 8 sulfurs, I still only have just sulfur, right? There's no other element combined there. So the oxidation number for that is just 0. Okay, so A was negative 2, B, the oxidation number is 0. Okay, then SCl2. Okay, so we know that the halogens are negative 1 unless they're paired with fluorine or oxygen. So we can say chlorine here is negative 1. We don't know what sulfur is. So negative 1, and there's 2 of them, so we times 2. And we can set that equal to 0. So here, x is equal to a positive 2. Okay, so sulfur is equal to a positive 2. Okay, on D, we have Na2SO3. Actually, I'm running out of room. I'm going to hop over here. So Na2SO3. Okay. Okay, so here we have a metal with nonmetal, so it's an ionic compound. So here I can just use the charge of my metal, my sodium. So sodium has a +1 charge, and we have 2 of them, so we're going to multiply by 2. We're looking for the oxidation number. I keep saying charge, sorry. The oxidation number of sulfur. So we're going to put an X there, and then oxygen is negative 2, and there's 3. And we're going to set all that equal to 0. Okay, so we have a positive 2 here. We have a negative 6 here. Okay, so if I move my negative 6 over, I get a positive 6. And then if I take my 2 over and subtract, then I've got a 4. So the sulfur here has a oxidation number of positive 4. Okay, one more. Okay, this one is sulfate, so it's an ion. We have a charge, so we know it's an ion. Okay, so SO4, negative 2. And again, we're still solving for sulfur. The oxidation number for sulfur. So we're going to put X, and then oxygen's oxidation number is negative 2, and there's 4 of them. So negative 2 times 4. And then since it has a charge, it's a polyatomic ion, we're going to set that equal to the charge on the polyatomic ion. So just rewrite that down there. Okay, so negative 2 times 4 is negative 8. And if I move that over here and add, then I'm going to get a positive 6. For the oxidation number of sulfur. Okay, so we're going to use these oxidation numbers to determine what is being oxidized, what is being reduced. So we'll do some of those examples here in just a second. Okay, so it says, is this an oxidation reaction? So iron, since it's by itself, is 0. Oxygen's by itself, so it's 0. Iron 3 oxide is an ionic compound, so we can just use its charges. So we have a positive 3 for iron and a negative 2 for oxygen. So you could go ahead and, we've been multiplying by the subscript, but it's easier just to leave them like this because it's not going to change anything. So going from 0 to 3, we're getting more positive. So we've lost electrons. So this was iron was oxidized. And then oxygen, we have going from a 0 to a negative 2. So it's getting more negative. So it was reduced. Okay, oxygen was reduced. Okay, so not, it's already somewhat complicated now. They got to throw in one more thing to complicate things. So we can say that iron was oxidized, oxygen was reduced, or I can say that iron is the reducing agent and oxygen is the oxidizing agent. So now why we say that is because the agent part of it is completely opposite. Okay, so if something's being reduced, it's because the other thing was oxidized. So we call the oxidized element the reducing agent because it's allowed for the reducing to take place. But remember, they go hand in hand. Okay, so if something was reduced, we say it was the oxidizing agent because it took those electrons. So that can get a little confusing. Just be careful with that. All right, let's do these problems. Okay, so we're going to figure out what is reduced, what is oxidized, and then we'll figure out the agents. Okay, so first we have potassium is all by itself, so it's 0. Okay, hydrogen is with oxygen, so hydrogen is going to be a positive. So positive 1, but there's 2 of them. And then oxygen is negative 2. Okay, potassium is for an ionic compound, so we can just use its charge, which is a +1. Oxygen is a negative 2. And here, this one's a little confusing because hydrogen is with a metal and a non-metal. But to get it to 0, we can just say it's +1, right? Because we want the compound to add up to be 0 if it's neutral. Okay, and then hydrogen is just 0. So now we've got to figure out what was oxidized, what was reduced. So I'm going to come down here. Potassium went from 0 to +1. Hydrogen went from +2 to +1. And then we have oxygen. Oxygen's going from a -2 to a -2. Okay, so we can say oxygen wasn't oxidized or reduced. Okay, so we're going to ignore that one. Okay, the numbers didn't change. But potassium is getting a little more positive. So it's oxidized. It lost electrons. Okay, and then hydrogen's getting a little more negative because we go from a +2 to a +1, so it's reduced. Okay, but now we can throw in the oxidizing agent, reducing agent. So here we would say that potassium is the reducing agent. Okay, And then hydrogen was reduced. But whenever we use the agents, we use the entire compound. So instead of just saying hydrogen was reduced or hydrogen is the oxidizing agent, we say water. So whatever that element is, whatever compound, that's what we're going to use. So we're going to say water is the oxidizing agent. Whoops. Okay, so just be careful with those. Okay, I'm gonna switch over here and do the next one. Okay, so we have iodine, bromine, we cannot get that to go. Okay, iodine plus bromine, the -1, going to 2 iodine with a negative plus bromine. Okay, so iodine is 0 because it's by itself. Bromine is 0. Okay, now they've written the equation in ionic form. No, not ionic, net ionic form. So it's not showing the spectator ions. So that's okay. We just want to see what happened in the reaction. Okay, so we can just look at the charges. That are given to us. So iodine goes from a 0 to a -1. Bromine goes from a -1 to a 0. So iodine's getting more negative, so we can say this one is reduced. And oxygen is getting more positive, so we can say this one was oxidized.